Hi everyone, welcome back to Princeton and welcome to our PSSCMP summer school. It's good to see you all again today. And two announcements before we get started. The first is that our previous email account, psscmp@princeton.edu, the technical issue has been resolved. And if you have any questions, please send your questions to this email account. And the second is, at the end of our talks, if you have any questions and want to talk to our speaker directly, please click at raise your hand so that we can promote you as a panelist and you can talk to our speaker directly. And today we are very greatly honored to have Professor Mak from Cornell University joining us. Professor Mak's group is one of the leading groups in exploring the physics in 2D materials and 2D heterostructures. And today he's going to talk about controlling spins in 2D layered materials. Professor Mak, it's all yours now.
Okay. Thank you for the introduction. I'll share the screen now. Okay, and is it okay? Can everybody hear me? Okay, let me make sure that I can only show the arrow. Okay, I hope also you guys can also see the arrow here. And thanks for joining my talk via Zoom. And today I will be talking about the first lecture on magnetism in 2D quantum materials. And specifically what I will be talking about today morning and tomorrow morning is that I will be talking about magnetism in basically 1 to 2 atomic monolayers of spins, so that the spin density is actually a very small compared to conventional bulk material. And there's a very small amount of spins in the system. And it turns out that because of this fact, there are interesting things that we can do. And today, there are two classes of these materials. One is actually just natural layered magnetic materials in the monolayer or bilayer limit, or we call it in the 2D limit. So these materials are basically magnetic in the bulk to begin with. And what we do is actually that we exfoliate them down to the monolayer limit and then explore the physics. And the second class of material that I will actually cover tomorrow is Moiré superlattices built on non-magnetic material. But it turns out that once you build this kind of Moiré superlattices and you form flat electronic bands, and that can greatly enhance the Coulomb correlation effects in the system, and you can get interesting magnetism from this kind of superlattice structure. And that will be tomorrow that I will talk about it. Okay. And first of all, why are this a class of materials interesting? And the first thing is actually that because of the fact that the number of spins is very small, right? The amount of spin in the system is very small. We make the amount of material extremely small, and the material is very thin, so that it's actually highly susceptible to perturbation, to external perturbations. And it's very controllable and tunable, for example, by electric fields or by doping, or by mechanical strain that we can actually apply to the system. And the level of control that actually I hope you'll be able to see tomorrow, that the level of control in Moiré superlattices is actually unprecedented. By just simply applying a voltage of 1 volt or something like that, then you can actually change the system from being ferromagnetic to non-magnetic to anti-ferromagnetic, right? And by just controlling the filling of each a Moiré band, that I will cover that tomorrow. And the second thing why these systems are actually interesting, because in the 2-dimensional limit compared to the 3D case for conventional bulk material, is that the spin fluctuations are significantly enhanced, especially near the critical points. And this actually provides an ideal avenue for us to actually directly control and see these fluctuations in 2 dimension. And not only thermal fluctuation, but hopefully we can also see quantum critical fluctuations of the spins once we go to 2 dimension and enhance the degree of fluctuations. And I'll give an example on this today. And finally, these systems actually are atomically flat, and their surfaces actually can be made to be extremely clean. And so it opens up a very interesting possibility to engineer new physics via heterostructures. And for instance, it can be interfaced with other non-magnetic quantum materials such as topological insulators and superconductors to engineer new type of physics that has atomically clean substrates interfaces, but at the same time, we don't actually have lattice mismatch problem like in conventional techniques, such as sputtering techniques and MBE techniques. Okay, so I'll begin with our discussion on the control of spins by electric fields and two-dimensional magnetic materials. And when we talk about magnetism in two dimension, there is always this myth of Mermin-Wagner theorem, which was proposed by David Mermin and Herbert Wagner in the 1930s, actually a long time ago. And it states the following, that continuous symmetries cannot be spontaneously broken at finite temperature in systems with short-range interactions in dimensionality less than or equal to 2. And the reason for that is actually because of the very low energy cost to create very long wavelength fluctuation for continuous symmetry systems. And so the system at any finite temperature will actually prefer to increase the entropy to minimize the free energy rather than staying in order state. Okay, and since magnetism actually is usually since short-range exchange interaction is responsible for magnetism, so we may wonder whether actually magnetism actually can exist in dimensionality equal to 2. But it turns out that in reality, I just want to point out that it's hardly relevant, the Mermin-Wagner theorem, because for most of the materials, almost all magnetic materials, you have certain degree of magnetic anisotropy, so that the condition that is a perfect continuous symmetry for the spin system is violated to begin with. And also the amount of fluctuation, the degree of fluctuations is actually diverging very slowly with sample size. For instance, it's a very slow logarithmic divergence. So if you're dealing with a finite size sample, especially, for instance, from micron scale samples in an exfoliated magnetic system that we are going to talk about, once we have a finite size system, the Mermin-Wagner theorem actually hardly matters. And so as a result, it's actually not very surprising that people have demonstrated magnetism in 2017, very robust magnetism down to a single atomic monolayers. And these are the two papers reported this observation in 2017. And this is as two-dimensional as you can get, because it's only a single atomic layers of spins. Okay.
Sorry to interrupt you, Professor Mak.
Yeah.
One question from Chen Li. What is the origin of magnetic anisotropy to escape Mermin-Wagner theorem in moraine magnets?
In moraine magnets, for instance, that we will talk about the system that we're dealing with, it's a spin-orbit interaction. And but for graphene systems, you can also have magnetism in acoustic bilayer graphene systems. And the spin-orbit interaction is actually not important in that situation. But turns out that actually the magnetism in graphene is originated from orbital magnetism. Basically is due to the Berry curvature in two dimension. And the vector of the Berry curvature is only along the outer plane direction.
Okay, thank you.
Okay. And ever since these two studies reported magnetism in monolayers of material, people actually, there's sort of an exploded activity in exploring other 2D layered magnetic materials in the monolayer limit. There's actually a large class of these materials now. There are actually hundreds of them, and maybe even more. And for this talk, I will particularly focus on this class of material called the transition metal trihalides. And the halide group is coming from the chlorine, bromine, and iodine. Okay, and it forms compound with transition metal atom, mostly from the 3D row in the periodic table. And also to confine the talk even further, we will only focus on two specific compounds which form from the chromium atom, magnetic ion, is chromium iodide or chromium tribromide. And in the monolayer form, you can actually see this is the crystal structure of a monolayer chromium iodide or chromium bromide. And the gray balls here is representing the chromium magnetic ion. It's surrounded by six halide atoms. Okay, and each chromium ion actually donates 3 electrons to the surrounding halide atoms, and so that it forms a chromium 3+ magnetic ion. And the chromium is sitting in a octahedral coordination so that the crystal field split the 3D orbitals of the chromium into the T2G and EG level. And we only have 3 electrons left. It's donated 3, and we have 3 electrons left in the magnetic chromium ion, so that basically all of the electrons will just fill in the lower T2G orbital with their spins all lined up according to Hund's rule. And furthermore, because of the spin-orbit interaction, especially in iodine compound, you know, iodine is a quite heavy element in the periodic table, so that we cannot ignore the spin-orbit interaction in this case, that the spin actually is locked to the outer plane direction by a rather strong magnetic anisotropy or spin-orbit interaction in the system, so that there's actually a large gap in the spin wave excitation in this particular material, and we can effectively treat it as a 2-dimensional Ising magnet when we, you know, apply a very small magnetic field or even no magnetic field in in-plane direction. And this is an example of the magnetic circular dichroism, or you can think of it as a magnetization of the sample of a monolayer of chromium iodide as a function of magnetic field. It's first reported in 2017, and subsequently it's been also reproduced by other groups, including our group. And you can actually see a very clear hysteresis loop, ferromagnetic hysteresis loop, that just by applying a small magnetic field, you can flip the spin from spin up to spin down. Okay. And one interesting characteristic for all these layered magnetic materials is that the exchange interaction is very anisotropic. In particular, the in-plane exchange interaction is very different. Usually, it's much bigger compared to the outer plane exchange interaction. And there are interesting things actually happen in the interlayer exchange as well, or the outer plane exchange interaction. And for instance, if you stack 2 of these monolayers together to form a bilayer, and the magnetism actually depends on the stacking structure of the crystal. For instance, in the monoclinic stacking sequence, if you stack the 2 layers in the monoclinic stacking, the spins actually couple to each other in the layer in an antiferromagnetic exchange interaction, so that at small magnetic field, you can see the data here that we almost have no magnetization in the system because it's an antiferromagnet. But once you apply a magnetic field that is on the order of 0.6 to 0.7 Tesla, you can cause a spin flip transition that you flip the spins of one of the layers and actually make it a ferromagnet. You can fully saturate the spins in the system. And on the other hand, if you actually stack the 2 layers in the rhombohedral stacking, that for instance, you can achieve by applying pressure to the monoclinic stacking material, and it turns into a ferromagnetic interlayer exchange. So typically what I want to point out is that from this measurement, typically the intralayer exchange, you can obtain from the measurement of the Curie temperature that you know the intralayer exchange is on the order of few milli-electron volt. But from the magnetic field dependence measurement here, that you can actually obtain a outer plane exchange interaction between the layer or the perpendicular exchange to be about a factor of 10 or even less compared to the intralayer exchange interaction. So the exchange interaction is very anisotropic in this system. Okay, so well, it's a relatively simple system. It's nothing like, you know, spin liquid, that kind of complicated system. But you will see that when we actually make the material very thin, even for this simple ferromagnets or antiferromagnets, we can actually play lots of fun things on this system. And this is the outline of today's talk. I will demonstrate, I will tell you 3 things if I have time. If I don't have time, I'll skip the last topic. First, I will tell you actually how we can control spins in this system by electric fields and by doping. Okay, and then second is that we actually will tell you a recent experiment in our group that we actually have invented a technique to directly see critical spin fluctuations in this 2-dimensional magnetic system, and we can only directly see it, but we can also use electric field to control these spin fluctuations and do something like a Maxwell's demon. And finally, I will highlight, if I have time, I will highlight another unique aspect of this kind of materials is that actually it can form atomically clean interfaces with superconductors and have some interesting observations as well. Okay, it's trivial that a magnetic field can control the spin in a magnet, right? But it's actually much less trivial to use electric field or a current to actually control spin in a system, simply because spins do not directly couple to electric fields in most of the materials. Okay, but people are extremely interested in controlling spins using voltage because it's very useful for writing a magnetic memory, writing a bit of information in magnetic memory devices. And currently, the most efficient technology is based on current-controlled internal magnetic interactions. Actually, you don't really want to, just build a wire near this magnetic bit of information and apply a current to the wire and generate a magnetic field to switch the magnetic bit of information, because that's extremely energy consuming. Okay, you don't want to do that. And currently, the most efficient technology is based on, rather than a current-induced external magnetic field, is actually based on current-controlled internal magnetic interaction. For instance, the exchange interaction or the spin-orbit interaction. And two techniques, most effective technique known nowadays is spin-orbit torque technique or the spin transfer torque technique. Okay, but in both of these techniques, although it's already very efficient, the spin current is actually produced by a charge current. The concept of this kind of devices is that you pass a charge current that will produce a spin current. If the spin current is large enough, then you actually be able to switch the magnetism or the magnetic state of one of the magnetic layers. Okay, and since a charge current is involved in this kind of technique, there is always an issue with Joule heating, so that you always produce lots of energy in switching one bit of magnetic information. And you can actually estimate how much energy you need. It's about 1 billion kT. kT is the room temperature energy scale. That's how much energy you actually need in order to switch one bit of information. And it's extremely inefficient, even with improvement compared to using bare magnetic field. Okay, so
sorry to interrupt you. There is one question.
Sure.
So the question is there any other factors that are responsible for switching from antiferromagnetic to ferromagnetic? Because what I can see that only small field is required to switch it to ferromagnetic states.
Is it talking about this particular system, right? Not talking about the magnetic devices, because there's no antiferromagnet typically involved in the other devices.
Yeah. He said like it's monoclinic system.
Yeah, so it's a particular, this a chromium iodide sample. So it's basically, you can consider it as a competition between the Zeeman energy term, because the ferromagnetic state or the fully spin aligned state actually can develop a Zeeman energy under a magnetic field. And the antiferromagnet actually cannot gain the Zeeman energy term, but it has an antiferromagnetic exchange. So basically, once you apply a magnetic field that overcomes the interlayer antiferromagnetic exchange, you can flip the spin because of the Zeeman energy gain. You can flip the spin from anti-parallel to parallel. And as a result, you can actually use the magnetic field that you determine to actually estimate the interlayer exchange interaction in this system. Basically, the magnetic field is just the field that's required to overcome this interlayer exchange.
Thank you.
Yeah, it's purely just Zeeman. Okay. All right. So this issue with Joule heating, and wouldn't it be nice actually if you can just use pure electric field to control the magnetic states in the system, so that it can actually provide much more efficient power consumption, operation for the system. And basically, all you need to do is just to charge a capacitor to apply an electric field. And the energy required for switching is to really just to charge and discharge a capacitor. And it will produce an energy that is orders of magnitude smaller compared to the current technology. And the two-dimensional magnetic materials with a very low density of spins actually would make the material very sensitive to gating. Is an ideal avenue to explore electric field controlled magnetism. But electric field typically do not couple directly to spins, but in certain class of material known as magnetoelectrics, and they can actually couple, the spins can actually couple to electric field. And simply speaking, the magnetoelectric effect is the following, is the generation of a sample magnetization by an electric field, or vice versa, or the generation of electric polarization by a magnetic field. So that means actually in this class of magnetoelectric materials, there's a direct coupling term between the magnetization and the electric field, or the electric field and magnetic field in the system. And this phenomenon is also of great interest recently in topological physics, especially in the class of materials known as axion insulators. And phenomenologically, one can describe the magnetoelectric effect with a free energy that has this form here. And this is the non-magnetic part, F0. And these two terms are related to this second term is the ferroelectric contribution. This is the ferromagnetic contribution. And then these two terms are simply the electrostatic and the magnetostatic interaction. And what's relevant for the magnetoelectric effect is actually the last term, the coupling constant alpha ij that can directly couple the electric field and the magnetic field in the system. And we have ignored all the higher order terms in this expansion of the free energy because that's sufficient for our discussion purpose. And to obtain the electric polarization or the sample magnetization, this is of the most interest to us. You just simply take the partial derivative of the free energy with respect to magnetic field, and you'll be able to get an expression for the magnetization. And you can see that in addition to the spontaneous magnetization and the induced magnetization by magnetic field, there is an extra term here, which is proportional to alpha ij times EI, which is basically is the magnetoelectric effect that an applied electric field can generate a magnetization in the system. And there's specific requirements. I see another question, but let me finish on this symmetry argument first. This specific symmetry requirements on whether on the value of this alpha ij, whether it's 0 or not. And it turns out that alpha ij is 0 if the system has both inversion and time reversal symmetries, have both, okay? And you can see that pretty easily. If the system has inversion symmetry and you perform an inversion operation on the system, it will change the sign of the electric field, but leave the sign of the magnetic field unchanged, okay? And since the free energy is invariant under an immersion operation, because it's immersion symmetric, and the alpha ij has to also change sign in order to keep the free energy the same. And that would mean that alpha ij is equal to negative alpha ij, and it has to be 0, okay? And the same argument also apply for time reversal symmetry, and except in this case would be that the magnetic field will change sign, but the electric field will not change sign. Okay. All right. So basically, in order for the magnetoelectric effect to be non-zero, we need a system to break both inversion and time reversal symmetries. That's the simple message. Is that the question that I can?
Oh, yes. So there is a question from Pavel. Are there examples of 2D Heisenberg or XY magnets? Could the cuprate parent compounds be interesting in this regard?
I think there is no material that is exactly like the Heisenberg model or the XY model. You can actually have a two-dimensional magnetic system that has an in-plane anisotropy, meaning that the spins are aligned into the plane. But since you are still sitting in a crystal lattice structure, the spin still has the tendency to be actually locked to some particular crystal orientation, rather than completely isotropic like in the XY model. But it actually, I think there are studies that are showing that in this type of system, as long as you have in-plane anisotropy, the magnetism is indeed weakened in the two-dimensional limit. So there is indeed some effects from magnetic anisotropy in the system. And whether cuprate is interesting in this regard, I think so. Yeah, it's a, we know that for undoped cuprates, it's a antiferromagnetic insulator. And it would be actually pretty interesting to study, the magnetism and how superconductivity evolves from the magnetism if we can just use a gate voltage to control the electron density in a two-dimensional sheet of cuprates, right?
Thank you.
Very interesting. Okay, back to our story. Broken inversion and time reversal symmetries are required for the magnetoelectric effect. And and in two-layer chromium iodide, as we have shown, the ground state is an antiferromagnet with the spins on the two layers actually anti-aligned with each other. And it turns out that in terms of the crystal structure, there is an immersion center in between the two planes. For instance, the immersion center is at this point here. So if you perform an immersion operation, you will bring this particle down to this particle. And without considering the spin, you would say that, oh, the system has immersion symmetry. But if you consider the spin, the immersion operation does not flip the spin. And this electron will move to the other layer with a spin down spin. Okay, so the system, when you include the spin, it actually breaks immersion symmetry. And because it's an antiferromagnet, it's obvious that it breaks time reversal symmetry, so that we actually have both of these requirements fulfilled in a bilayer chromium iodide sample, so that we would expect that, a very efficient platform to explore the magnetoelectric effect or the electrical control of spins in this type of system. For instance, a naive way of thinking how an electric field can possibly control spins in this system is that if you apply a perpendicular electric field, and some of the electron will be able to transfer from the top layer to the bottom layer. And because the intralayer exchange is so much stronger, then the spin of this from this top layer has to flip when you go to the bottom layer. And effectively, you just flip one spin from spin down to spin up, and you generate magnetization, but just simply applying an electric field in this charge transfer mechanism. Okay. And this is a particular sample. So in order to explore this effect, Shengwei Jiang, a postdoc in our group, has fabricated this type of structure from mechanical exfoliation. In the center here, there is a bilayer chromium iodide sample. It's encapsulated between hexagonal boron nitride, and they are insulators, and they're atomically flat insulators, so you can actually form very clean interfaces. And they're extremely good insulators, so that you can actually use it as a gate dielectric. And to form electrical gates, we further put graphene electrodes at the top and the bottom, so that you can apply a voltage at the top and the bottom and try to introduce carriers and apply an electric field in the system. It's basically a parallel plate capacitor, what we have made here. Okay. And this, on the right, it shows an image of the finished device. The gray dashed line here is just outlining, the location of the graphene gates. And this is a zoom-in view of the sample, which is a bilayer chromium iodide. And in our experiment, we shine light into the sample. And what we look at is actually, we look at the absorption difference between the left-handed light and the right-handed light. Because it's a magnetic material, it will absorb light differently for left-handed light and right-handed light. And the signal is called the magnetic circular dichroism. It's a difference between the absorption between left and right circular polarized light. And the signal is proportional to the sample magnetization. So it's a very efficient way to measure sample magnetization or magnetism in this kind of materials. And it's also very volatile, because all you need is just some optical components. Okay, this is the data that shows the evolution of the magnetization of the system under different applied electric fields. And on the y-axis shows the magnetic circular dichroism signal that is proportional to the magnetization of the sample. The x-axis is the magnetic field. And we can see that when we apply when the system is under zero electric field, 0 volt per nanometer, and you can see it's basically an antiferromagnet with nearly zero magnetization under small magnetic field. But once you apply a magnetic field that can overcome the interlayer exchange interaction, the spin can actually be flipped to be parallel to each other. We call it a spin flip transition, or it's actually a special class of metamagnetic transition. And as you increase the electric field, you can actually see that while the magnetization in the spin aligned state, a large magnetic field remains almost unchanged, the magnetization actually in the antiferromagnetic state actually opens a gap, right? What it means is actually that an electric field can actually generate a magnetization in the antiferromagnetic phase. We can do it, do a more careful electric field scans. For instance, we park the magnetic field at 0 Tesla so that we know the sample is at 0, is in the antiferromagnetic state. And as we scan the electric field, the magnetization just increases linearly with the electric field. And this is for instance, the up-down configuration of the antiferromagnet. And if we prepare our antiferromagnet in the down-up configuration by, for instance, stripping the magnetic field all the way to -1 Tesla and bring it back to 0 Tesla, then we prepare our system in the other configuration of the antiferromagnetic state. And in this case, the magnetization can still be generated by electric field linearly, but the slope of the dependence is actually reversed. And now if you apply a magnetic field of 1 Tesla that fully saturate the spins, and you can see that basically the magnetization is almost independent of the electric field. Okay, and we can actually compare this result in the bilayer chromium iodide with a monolayer of chromium iodide, which only breaks time reversal symmetry, but the system has inversion symmetry because of the 6-fold rotation symmetry of the chromium atom. And you can actually see that there's a negligible effect on the magnetization of the system under an electric field. So we have observed no magnetoelectric effect in the monolayer of chromium iodide. And all of this observation actually can be easily understood from a symmetry point of view. For instance, let's begin with the antiferromagnetic states with a spin oppositely aligned for the 2 layers, either this state or that state, right? So in this case, we have said that, the immersion symmetry is broken, time reversal symmetry is broken, so we actually expect magnetoelectric effect. And indeed, we also have talked about a simple model based on charge transfer that you apply electric field, the charge can move from the top layer to the bottom layer and flip the spin and generate the magnetization. And indeed, we can actually estimate, based on a capacitive model, estimate how much spins that can be transferred from the top layer to the bottom layer under an electric field. And the slope that we can actually produce by this simple estimate agree reasonably well with the experimental observation. Of course, with some uncertainty that, it's not a direct measurement of the magnetization using our technique, right? Effectively, in our measurement, we are measuring the Hall conductivity in the optical region rather than directly measuring the magnetization. So we have some uncertainty in terms of converting into the magnetization. And on the other hand, if you fully saturate the spins in the system into the ferromagnetic states or the spin aligned states, in this case here, and it's not hard to actually figure out that inversion symmetry is actually preserved in this particular case. For instance, if you move the immersion center is in between the layer here, and if you perform an inversion operation that brings the electron from the top layer to the bottom layer without flipping the spin, it reproduces the crystal structure. Okay, so that another naive way of thinking is that if you apply an electric field, even you have charge transfer because of the spins of the 2 layers already aligned, so you don't generate extra magnetization. So that this is fully expected from both the symmetry point of view and also from this naive picture of electric field induced charge transfer between the 2 layers. Okay, now we actually can indeed generate a magnetization in the sample using electric field. And now we can actually demonstrate something also quite fun, is that if we park our magnetic field in near this spin flip transition field here, and the spin is actually quite unstable, near this transition field here, and we actually would expect that, the electric field can have a large perturbation on the system because we are parking the magnetic field near the unstable point. And indeed, if we park our magnetic field near this spin flip transition field and scan the electric field in our gates, and we can actually induce continuously and also repeatedly a transition from the spin aligned state to the antiferromagnetic states. Okay, and you can do many switching as you like, that is demonstrated in the bottom, and the device just keep functioning. Just keep applying the cycles of the electric field. Okay, so we can, in principle, what we have demonstrated here is actually that we can use electric field to switch the spins or switch the magnetic states of the system. And that actually is quite interesting. You just need to apply a voltage and to flip the spins. And it may also have, some technological relevance. But you may say that, wait a minute, you may be cheating because actually it's not purely, electric field switching of magnetization. You actually have to apply a magnetic field in order to do that, right? You have to bias the sample with a magnetic field near this unstable point. And it's a reasonably large magnetic field. Actually, you don't really want to use it in your magnetic memory devices because it's a 0.7 Tesla magnetic field that you need to apply to your device in order to switch the spin. So the question is actually that can we really realize a zero magnetic field switching in our system? And to answer this question, we actually go back our gate device structure, which is basically a parallel plate capacitors, as I mentioned. And what we have discussed so far is that we have actually applied electric field to the bilayer chromium iodide sample by something called anti-symmetric gating. What we have done here is actually that we apply a positive voltage to the top gate and then a negative voltage to the back gate. Okay, so that we do not actually effectively introduce charge carriers into the system. We only introduce electric field through this bilayer system, and we have seen the magnetoelectric effect in this configuration. But we can also use symmetric gating, for instance, applying positive voltage at both of the gates without introducing electric field into the system, and apply doping into the material. And maybe actually that's a more effective way of changing the magnetic exchange in the system. Okay, and to see how this works, let's just focus on a monolayer chromium iodide sample first. And what we show here is the AC susceptibility measured as a function of temperature for a monolayer of chromium iodide. And just a few words on measuring the AC susceptibility. What we have done here is actually we apply an AC magnetic field into the system so that it modulates the sample magnetization, and we detect the modulated change in the magnetic circular dichroism signal that's measured by optics. And so the measured signal is proportional to the AC susceptibility in the system. And indeed, the temperature dependence is also expected as expected for the AC susceptibility of a ferromagnet. It actually shows a pronounced peak in the susceptibility at the Curie temperature of the magnetic system. Okay, and what we show here is also we show the magnetic susceptibility measured at three different doping levels. The black curve here is for the case that there's no doping applied to the system. The red is we apply whole doping to the monolayer chromium iodide, which actually increases the TC, the Curie temperature of the system, by about 5 Kelvin. And if we reverse the sign of doping by introducing electron doping to the system, we actually decrease the TC by another 5 Kelvin. So that by simply applying doping via a voltage, we can actually create a tunable Curie temperature by about 20% change in the TC, or a total of 10 Kelvin. Okay, and it may seem actually that's not really significant effect because you only change by 20% at 10 Kelvin. In absolute energy scale, that's about 1 milli-electron volt. That you change the exchange interaction by 1 milli-electron volt in the system by just applying doping. But you have to remember that actually the exchange interaction in bilayer chromium iodide is actually very anisotropic. The in-plane exchange interaction is more than 10 times bigger compared to the outer plane or the interlayer exchange interaction in the system. So that if doping here introduced by the gate can change the exchange interaction by 1 milli-electron volt, that's actually big compared to the interlayer exchange energy scale. And we would expect actually something dramatic happening for the interlayer magnetic state, in the system. And maybe we can actually even perform zero field switching. And indeed, we can actually do that in our system. This shows the magnetization of the sample as a function of magnetic field again for a bilayer chromium iodide device, so that it actually is an interlayer antiferromagnet to begin with. And with increasing electron doping, you can see here that the spin flip transition field just shrink to smaller and smaller magnetic field. And finally, at large enough electron doping, it basically becomes a ferromagnetic system that it has almost a single loop of magnetization that is remained. Okay, and what we can also actually extract the exchange energy scale from the measured spin flip transition field. And this actually shows the measured, the extracted interlayer exchange energy versus gate voltage or the doping density. At the doping density about 10 to the 13 per centimeter square, which is actually not really a lot of carrier density applied to the system, you can actually see a change in sign in the interlayer exchange integral, and it's called an exchange inverse transition. So what's special in this system is actually that you can just use a voltage to control the material from being an antiferromagnet to a ferromagnet. Actually, you can also do it repeatedly. And effectively speaking, we have already achieved a zero field switching of the system from a ferromagnet to an antiferromagnet. Okay.
Sorry to interrupt
you.
I think we
can
answer one of the questions.
Yeah.
One question from Powell. Are the transport properties of chromium triiodide affected upon doping? Is it becoming more metallic?
In principle, it is, but it turns out that this material, the mobility is extremely terrible. And so nobody has been able to actually measure transport in this two-dimensional layer system, simply just because the mobility is so low. And part of the reason is also that the electron mass is actually very high because of the flat 3D band in the system. So, and also maybe the material quality is not very perfect at this point. And so that actually nobody has been able to measure in-plane transport in the system. But that's a very interesting question because it's a semiconductor. You dope it with charge carriers and you should be able to get some transport, but yeah, it's limited by mobility at this point.
Okay, so one more question from Ashutosh. Is there any effect of doping on local symmetry distortion?
That's an interesting question. Nobody actually knows whether there is a distortion in the crystal structure or the symmetry of the system by applying doping. But having said that, there's certainly a symmetry change in the system when you take into account spins, right? For instance, in this example here, a gate-induced exchange inverse transition, the system is non-central symmetric or breaks the inversion symmetry in the antiferromagnetic phase. But once you apply a doping large enough to convert into a ferromagnetic phase, the immersion symmetry is restored in the system. So in some sense, it's also a gate control symmetry, but it's not really, there's no clear evidence from our results or from other studies that actually show a clear crystal structure change introduced by gating.
Okay, thank you.
Okay, all right. So what we have demonstrated here is that actually the doping can effectively tune the magnetic interaction in the system, in particular, the interlayer exchange interaction in this bilayer chromium iodide sample. But what so far we have demonstrated is actually that we are just tuning the static magnetic properties by this gating technique. And I just want to very briefly highlight that not only the magnetostatic property is actually changed, but the dynamic property of the spins can also be modified significantly by gating. And this is the work by our former postdoc, Xiaoxiao Zhang, who is now a faculty at University of Florida, physics. And what she did here is actually to initiate spin wave excitation in the system by a pulse optical pumping, and then probe the subsequent magnetization of the system by measuring the curve rotation signal as a function of the time delay between the pump pulse and the probe pulse. And you can see that after the pump pulse impart on the system, you can actually create some coherent oscillation in the magnetic signal or in the magnetization of the system. That is actually very systematically dependent on the magnetic field. We know that it's spin wave because of this magnetic field dependence into the system. And if you Fourier transform this measured a time domain signal into the frequency domain signal, you can see a clear antiferromagnetic mode that is due to the spin oscillation in the antiferromagnet located at a sub-terahertz frequency, close to 100 gigahertz frequencies. And by applying gate voltage to the system that introduce hole doping or electron doping into the system, you can actually see that there's a clear shift in the spin wave frequency in the system by tens of gigahertz frequencies. So this also is an interesting way to actually control not only the magnetostatic property, but also the spin dynamics into the system, And maybe it's actually of a potential interest in making some gate-defined magnetic metamaterials in the future. Okay. So that's pretty much the part with electric field control spins. And actually, with the time remaining, maybe I can only talk about the second part of my talk, which is directly seeing the critical spin fluctuations in 2 dimension. Okay. And so the critical spin, a brief introduction on critical spin fluctuation. The simplest model to understand magnetism and especially ferromagnetism in a system is the mean field model, that we can think of it each magnetic ion, for instance, this green ball here at the center of this cube. Each magnetic ion is actually surrounded in high dimension system, for instance, in 3D, right? Each magnetic ion is actually surrounded by many other magnetic ions in the system. The other magnetic ions, the other green balls or the purple balls here, will produce a mean magnetic field into the center magnetic ion. And that's the mean field picture. As a result of many surrounding neighbors in high dimensional systems, there's actually negligible fluctuations of the mean magnetic field from its mean value, right? From the magnetic field from its mean value. So that we typically would expect that the mean field picture to be correct in high dimensional system. Of course, the detail still depends on the magnetic anisotropy, whether we're talking about Ising spins or Heisenberg spins. Well, the situation actually changed dramatically if you go to a lower dimensional system. And let's consider as a simple example, the extreme case of one-dimensional system. Now, each magnetic ion is only surrounded by two other magnetic ions in the system, okay? So there are only two of them, and you would expect that with so few magnetic ions surrounding each other, and the fluctuation of the magnetic field that is produced by its neighbor is actually significant compared to the mean field value produced. And we would expect very strong fluctuation effect in a low dimensional system. And in fact, the mean field picture would completely break down in the 1D system, that there's actually no long-range order, no long-range magnetic order is allowed in a one-dimensional system because of these large fluctuations from the mean field value. And since we are talking about a system that is close to be described by an Ising model, so we will talk about a little bit more about what we would expect in a two-dimensional, in an Ising model system. And that's what here is what's known for an Ising model system. For dimension that is bigger than 4, which is known as the upper critical dimension for an Ising model system, that the prediction is actually that the mean field picture is valid. And in this case, the magnetization will scale with the reduced temperature with the power 1/2, and the magnetic susceptibility will just follow a form that is basically the Curie-Weiss law. Okay. So above dimension equal to 4 for Ising spin system, we would expect the mean field to be correct. On the other hand, in the extreme case is that below the lower critical dimension, which is equal to 2 to an Ising system, the fluctuation is so strong that it will completely destroy the mean field picture. And in fact, there's actually no magnetic order allowed for dimensionality less than 2 in the Ising model. And in between the dimensionality between 2 and 4, fluctuation of the magnetic order parameter is actually important. And so the exact behavior deviates from the mean field picture, but the long-range magnetic order is still allowed in between this dimensionality 2 and 4. So the most interesting scenario is actually sitting at the lower critical dimension here, dimension equal to 2. And the exact solution will actually tell us that long-range magnetic order is allowed in the system, but the mean field picture is actually significantly modified. For instance, the magnetization would now scale with the reduced temperature in the power of 1/8, and there's also a significant change in the power law dependence for the magnetic susceptibility. Well, you may say that, okay, this seems to be a rather insignificant change of the power law in the system, but let's actually do an estimate. Let's compare, when the magnetization or the order parameter or the mean order parameter decreases to about 50% of its zero temperature value. Okay, and let's look at the susceptibility enhancement. The spin susceptibility is basically a measure of the amount of spin fluctuation in the system. So the spin susceptibility enhancement in the mean field picture, when we increase the temperature to about 50% of the mean magnetization value compared to zero temperature, there's only a 4 times enhancement of the spin fluctuation or the spin susceptibilities in the mean field picture compared to zero temperature. And in 3-dimensional case, it slightly deviates from the mean field picture, but it's not that different. It's only 14 times enhanced compared to the susceptibility at in the zero temperature limit. But if you consider in the 2D case here, there's actually more than 10,000 times enhancement in the spin fluctuation in the system compared to the compared to the 0 temperature limit case. So the conclusion is actually that in 3D material, we would expect that actually the critical fluctuation will be rather difficult to access, but in a 2D, in the 2D limit, the critical fluctuation is significantly enhanced, especially near the critical point. Okay. And this shows a simulation, a Monte Carlo simulation of what we actually expect in a 2-dimensional Ising system for a temperature that is much smaller than the Curie temperature of the 2D Ising ferromagnet. And basically the sample is a single domain ferromagnet. The black line here would actually represent all the spins are lined up to the outer plane direction, say out of the page here, a spin up. And if you increase the temperature, but still far away from the TC, you can see that some of the spins, because of the excitation, will flip the sign to spin down. It's represented by the white dot here. And you can only see small patches of spins being anti-aligned. But when you get very close to TC here, you can see actually big patches of the sample that has spins anti-aligned from each other. Okay, and if you actually calculate the magnetization of the sample as a function of time in this system, at low temperature, the magnetization is actually very stable. It's almost independent of time. But once you heat up very near the TC, you can see actually big fluctuations of the magnetization of the system from up to down, and then actually a pretty slow time scale here. And this is actually expected in a critical phenomenon known as the divergent correlation time or the length scales near a critical point. Basically, the correlation, the spins are correlated at any time scale and length scales in the system. Okay, so the question is, can we directly see such critical fluctuation in a model system that is pretty much close to an Ising 2D magnet? And the system we are looking at is 2D chromium bromide. You may wonder why we actually switched to the bromide here instead of iodide. We can also see the same thing in iodide as well, but for some reason we actually have chosen chromium bromide for now. So this is a sample optical image of a monolayer of chromium bromide. You actually cannot see much because the optical contrast is very, poor in this system. But I convinced you that there's actually a piece of magnet there. Here is the measured magnetic circular dichroism signal as a function of the magnetic field. When we cool the sample below about 22 Kelvin, it turns into a ferromagnet, right? With a clear hysteresis loop that is seen in the system. And a glimpse into the enhanced fluctuation effect in the system can actually be provided from a measurement of the temperature dependence of the magnetic susceptibility, which is shown here, a comparison between a monolayer sample and a bulk sample, which is a 10 nanometer thick sample, but effectively speaking, it's a bulk material. And you can actually see that the magnetic susceptibility diverge much faster in the monolayer material. And if we plot the magnetic susceptibility as a function of the reduced temperature here, and you can fit the susceptibility by this power law, you can actually extract an exponent for the power law dependence in the bulk material to be about 1.2. And that is actually very close to the mean field case, right? In the mean field case, we would expect a Curie-Weiss law. And so the gamma exponent is equal to 1 exactly, and it's equal to 1.2 here. So it's not that far away from a mean field picture. But in the 2D chromium iodide, you can actually see that the exponent is actually, it becomes 2.4, it's significantly enhanced. It deviates a lot from the mean field value equal to 1. So this already provides a glimpse into the fact that actually fluctuation effects are much more important in the bilayer, in the monolayer limit, and that's reflected by the power law scaling of the magnetic susceptibility. But can we directly see this critical fluctuation by eyes, for instance? And this is the setup that we actually have built in our lab recently. What we do here is basically a curve rotation measurement in the sample, but with enhanced sensitivity, actually a lot enhanced sensitivity. So let me just briefly tell you how it works. This is incoming laser going through a first polarizer that we actually linearly polarize the laser into the system and just shine onto the sample with a microscope objective. This is the sample where it's located. But if you actually are interested in doing curve rotation measurements in your lab, you may actually have figured it out whenever you use a large numerical aperture objective, it tends to distort the polarization state of the incoming light a lot. Okay, so that's the fact. And what actually came up by this, by our postdoc Chen Hao Jin, and also our graduate student Zui Tao here, is that they actually come up with a clever technique that to use an extra lens to focus the light into the backside of the objective. And effectively speaking, we are using a very small numerical aperture to shine onto the sample. So it's a broad field illumination on the sample. And by using a very small numerical aperture, it turns out that the polarization state of the sample, of the light, can actually be kept very pure even after going through the objective. And then once the light actually interacts with the sample, because the sample is magnetic, the polarization of the light will be rotated by a small angle theta that is proportional to the magnetization in the system. And then the reflected light will be collected and then go through a second polarizer. We try to analyze this small rotation angle change and then image the whole sample by a camera. Okay, let me just briefly mention, if the polarizer 1 and 2 here, 1 is for the instant path, 2 is for the collection path, they are perfectly perpendicular to each other. And you can calculate that the optical contrast signal is proportional to theta squared. Okay, theta is a small rotation due to the magnetization of the sample. So it's a small signal squared, so it's even smaller. So that's not actually the ideal mode for detection of the magnetization of the sample, because it's a small number squared. And in fact, you can actually do it much better if you slightly rotate the polarization of the second polarizer by an amount, we call it phi. That is still a small angle, so it's much smaller than 1. We measure the angle in radian, so it's much smaller than 1. But this phi angle is much bigger than the signal that is produced by the sample theta. Okay. And in this case, you can actually calculate the optical contrast here. And it turns out that by just rotating a small angle of the second polarizer, the small signal can now be mixed to a bigger signal. The small signal theta is now mixed to a bigger signal phi here. And if we take a square of this, which is total signal, we will actually obtain an optical contrast that is proportional to theta over phi. Okay, now it's no longer a small number square, but it's actually proportional to a small number. And furthermore, phi is much smaller than 1, so that we would actually expect the optical contrast to be enhanced by many, many times. Okay, and in fact, we can actually enhance close to 1,000 times of the signal by just doing this apolarization control. And for those of you who actually have done a RF technique, microwave technique a lot, this is actually called a Homodyne detection technique. It's basically a small signal mixed with a big signal from a local oscillator. Okay, is it okay I use 5 more minutes?
Sure, like since you're already prepared, please keep going.
Yeah, I just showed the result and then I'll just end, yeah. And so this is basically the technique we use to detect. So let's see how it works. This is a monolayer, chromium bromide again, that with the spins prepared in the up state by applying an outer plane magnetic field and saturate there. And you can actually see a clear signal. This is the sample boundary of the sample, a clear, brighter signal compared to the substrate of the sample. And then here is the spins that is actually prepared in the down direction. And you can actually reduce optical contrast compared to the substrate in the surrounding signal. And the optical contrast actually with this enhanced polarization control technique can actually produce a 60% optical contrast for single layers of spins. So you can really see by your eye, after this correction, use polarization. And that actually allow us to take one shot of image in 10 milliseconds. So this is only a 10 millisecond exposure. We can actually even do faster if the camera is fast enough. And so by just exposing the sample to a few milliseconds, we actually can obtain an image of the spin. And with this fast imaging mode, now we can actually detect the critical spin fluctuation near the TC of the system. What I show on the left here is, so again, this is the sample that is prepared in the spin up state. So the signal is brighter compared to the background. And we heat the sample slowly from 18K to 26K. The TC is about 22 Kelvin in the system. And you can see actually near the TC, you can see crazy changes in the magnetization and then quickly disappear once we warm up above the TC and everything becomes stable again. But if we actually park near the TC, for instance, 22.1 Kelvin, and we are not doing anything to the system, right? This magnetic field is kept at 0, and we are not doing anything to the system besides watching. And you can see this crazy spontaneous fluctuation of the magnetization in this piece of a two-dimensional ferromagnet system. And if you move away from the TC, this fluctuation just quickly disappear. Okay. So if we actually park at a particular location and monitor the magnetization of the sample as a function of time, below TC, you will see the spin-up state here with 0.6 optical contrast, a very stable spin-up state, no change with time. But if you increase the temperature close to the TC, you can see lots of crazy fluctuation. That is actually quite similar to the Monte Carlo simulation I have shown you a few slides ago. And above the TC, the magnetization just goes to zero. We can analyze the data a little bit better. Basically, the central function that characterizes critical fluctuations is called the correlation function, which is actually the deviation of the measured value from the mean, right? So it's basically a measure of the fluctuation from the mean value. And if we set R1 and R2 at the same, we basically measure the fluctuation at one point only, but at different time delay. And we can calculate the correlation function as a function of time. And you can see that it displays an exponential decay in most cases, but very close to the TC, you can see significantly slow down of the critical dynamics. So you can see a much enhanced correlation time. By fitting the data with the exponential form, we can actually extract the correlation decay time on the right. And you can see 2 orders of magnitude enhancement compared to the non-critical value. So it can actually, the spin dynamics can become as slow as 1 second in this near the critical point here. And outside the critical point is 10 milliseconds, but that's actually limited by the speed of the camera only. Okay, so we can compare with the Monte Carlo simulation. Actually, the time traces of the magnetization are very similar to the observation, and you can also do a correlation. You can calculate the correlation function using this Monte Carlo results, and you can also obtain correlation function that is very similar to what we actually have obtained in our experiment. Okay, and I will skip that. And finally, I just 1 minute, and just want to say that we can also actually use this critical fluctuation to realize something like a Maxwell's Demon control on the magnetic state. And what we are doing here is actually that we can, what we have made is a gateable device that the monolayer chromium bromide can be actually gated to introduce doping into the system, so that we actually can change the TC of the system by a small voltage. For instance, a 0.5 Kelvin change in the TC by applying 1 volt voltage. Now, since the critical fluctuations is so much dependent on how close you are to the critical point, then if you just park at a particular temperature, for instance, at 18 Kelvin, that is below the TC of the black curve here, and just applying a gate voltage, you can actually turn on and off the critical fluctuation in the system. So here I showed the magnetization as a function of time, a varying applied gate voltage, and you can actually see that without applying any gate voltage, the magnetization is stable. But once you turn on even a 0.1 volt voltage, you can actually turn on the magnetization fluctuation in the system. And we can actually do something like a clever Maxwell's Demon, that if we want to switch the magnetic state from spin up to spin down, all we need to do is to actually apply a voltage to turn on the critical fluctuation. If the spin fluctuates to the point we like, say, spin down, then we just turn off the voltage and the spin will actually stay a spin down. If we want to switch back to spin up again, we just turn on the fluctuation again, it will switch back to spin up. Anyway, so this is the, something fun that we can play with this system. Anyway, so I don't have time to go through the rest of the talk, but let me just conclude here that, by making the magnet thin, you can actually do some fun things, quite fun things with even simple ferromagnetic or anti-ferromagnetic system. And, one possibility is actually that can we make an MRAM device with, an array of Maxwell's demons, for instance, that we actually have introduced. And there are some also interesting questions that can be raised, for instance, direct imaging of quantum critical fluctuation. Maybe we can actually go use, some gate voltage or magnetic field to cause some quantum phase transition, and can we actually directly image or see this spin fluctuation near a quantum critical point? So these are interesting questions, to be answered in the future. Okay, I can stop now and happy to take more questions. Yeah.
Thank you for your talk. And one of the questions is actually from an anomalous attendee, like he or she would like to be interested in to hear a few word summary of your third part, the third part of your talk, if possible. Could you go through it quickly, since you're already prepared?
Oh, the third part is about interfacing magnet with superconductors, and what we actually have seen here is significantly enhanced anisotropic magnetoresistance due to the interface of superconductor and magnet. And maybe just to boil down to the simple message is actually that because Andreev reflection is a spin-sensitive process, and if you actually have a superconductor that has spin-orbit coupling here, the spin triplet component in this superconductor will actually allow a spin flip Andreev reflection process that can happen. And also this spin flip Andreev reflection can actually be controlled by rotating the magnetization in the ferromagnetic material. So we can actually detect basically up to 100% anisotropic magnetoresistance in the sample because of this interface control of superconductor and magnetic system. That's just yeah. It's hard to explain further in detail, but it's like a 1-minute summary of that.
Okay, thank you so much. And so we have some questions here, and if we go back to the first question, I think that goes back to when you explained the magnetoelectric effect from the electron transfer, like the magnetism from back there.
Yeah.
So one attendee asked, so using this argument, is the magnetoelectric effect is forbidden in the trilayer?
Yeah. The trilayer, I have to think about whether it has a perfect inversion symmetry. I think the answer is yes, because the trilayer, it certainly has the, because it's actually, the trilayer would be, for instance, here would be spin up, you add a spin up layer here, spin down and spin up. But whether it has inversion symmetry, we still have to consider the atomic registry of the system. I haven't actually been thinking about carefully with the trilayer system, but I think my answer is yes, that it has inversion symmetry once you go there, and you're not allowed to have a magnetoelectric effect in the system. Yeah, that's a good question, but we actually have not tested in the trilayer sample.
Thank you. And for the next two questions is about Shenwei's first work. So the first one is, how large is the magnetoelectric coefficient in chromium triiodine compared to, for example, chromium oxide?
Oh, it's actually it's substantially larger compared to chromium oxide, and we have estimated. I don't have the slide to show here. Do I have the slide to show here? Sorry, I don't have the slide to show here, but it's actually in our paper that you can look up. We actually have calibrated the magnetoelectric coefficient alpha value here. It's rather big. It's not like a multiferroric system that big, but it's actually quite big. It's I remember it's orders of magnitude bigger compared to the magnetoelectric coefficient in chromium oxide.
Okay, thank you. And for the next question from Paul, at what frequencies are the measurements, I think it's still shown with this work, are this measurement carried out? Could the finite frequency cause contributions from the excitation of the magnets?
I guess, is it talking about the switching speed of the system, or? So what we are doing here, just in terms of scanning the electric field, this is scanning very slowly. So effectively it's a DC measurement. And even for the switching, you can see that the time scale, we are just doing a very slow scale switching, slow time manipulation. And it's an interesting question to actually to know, what is the speed operation limit for the system. When you actually apply voltages in the RF frequency, and you can potentially use the magnetoelectric effect to excite, spin wave modes in the system. But you can actually see that in this result here, we actually have measured the spin wave frequency in this system. Because of the antiferromagnetic exchange and the large anisotropy in the system, is rather high. The frequency is actually close to 100 gigahertz. So it's not very easy. It's actually very difficult to do with a conventional RF technique to access this frequency range. So I doubt that one can actually easily use RF voltages to actually create spin wave excitation in this system. It's difficult. It's not impossible, but it's difficult. Yeah.
Okay, thank you. And for the next question, so I think it's about Shenwei's second work, like the Nature Nano paper. So are these hysteresis a first order phase induced?
Which hysteresis? You mean here, right?
Yeah.
Okay. The spin flip transition is a first order phase transition, and so that it actually it displays a hysteresis. And actually, even for ferromagnet, you scan the magnetic field, there is a hysteresis. That's because that's also a first order phase transition from the spin up to the spin down state, and you have a hysteresis.
Okay, thank you. And also on this slide, so from Karsa, does the setting J perpendicular close to 0 also ruin the stability of the magnetic state? And would it be capable of storing the information?
Yeah, it's interesting to think about what's happening near the exactly J equal to 0 case here, because it seems that effectively speaking, the two layers are magnetically decoupled. And I haven't thought about, whether you can actually use it to store information, because that if the system is can be randomly fluctuating, independent of each of the layer, it may not be very useful in terms of memory storage. I don't know, but there's also, actually, I want to also point out one complication here is that even the exchange energy go to 0 at this point here, and you also have to consider the simple magnetostatic, which is basically the demagnetization field of a ferromagnet. So even at this J equal to 0 point, the system still prefers to be an antiferromagnet to reduce its magnetization, okay, of the system, because of the demagnetization energy. Once you have a magnetization in the system, you have demagnetization energy. So the system actually, even at perfectly J equal to 0, because of the magnetostatics, you actually still have an antiferromagnetic system. You actually have to go further beyond this value to really turn the system, from an antiferromagnet to a ferromagnet. And it would be interesting to see near this critical point here, but we actually, we have not done too much on it.
Okay, thank you. And also from Shiming, so for the ferromagnetic two-layer chromium triiodide, when the field is applied, the inversion symmetry is technically should be broken. However, why the magnetoelectric coupling is still negligible?
Oh yeah, so that would be a higher order effect, right? So basically in this AF expansion of the free energy, you actually have to include higher order terms because the alpha here is introduced by an electric field. So that would be a smaller effect, actually. So it would be what I'm saying here is actually whether there is a linear magnetoelectric effect happening. So at least for small electric field, there's no signature of a linear magnetoelectric effect happening. And maybe a large electric field, you do see a little bit deviation from the zero, a non-zero change in the spin aligned case, but it's hard to say at this point because it's a nonlinear effect. Yeah, you are right that the electric field can break the inversion symmetry, but it's a nonlinear effect.
Okay, thank you. So I think one question about the first part of your talk is from Tyler. So is it actually possible to induce some magnetization of the sample using gate voltage with no magnetic field?
Yeah, actually, this is what's been shown here, right? So the red curve and the black curve here is the induced magnetization perfectly under zero magnetic field.
Okay.
Yeah, and actually you can see that with large enough electric field, you can actually generate quite substantial magnetization because compared to the saturated magnetization, this is like 25% of the saturated magnetization. So you can actually generate quite substantial magnetization in the system by a simple electric field. Yeah, under perfect zero magnetic field.
Okay, thank you. And the next question about chromium triiodide is, what is the magnetism behind the antiparallel alignment at the interface of chromium triiodide bilayer? Is there any orbital contribution to the magnetism from chromium 3D orbitals?
I guess the question is, what is the mechanism responsible for the interlayer antiferromagnetic exchange?
Yeah.
And I think the chromium atom has to exchange through the iodine atom, and it's likely a double super exchange interaction in the system because the chromium atom is separated by 2 iodine atoms. So it would be, I think it's more like a super exchange mechanism, but it's a double super exchange because you actually have to go through 2 iodine atoms to do that. And so that's why actually the interlayer exchange is also rather weak in this system. That's one of the reasons it's a relatively weak double super exchange process.
Okay, thank you. And now I think we can move
but
to...
I cannot explain the sign of the why it actually is, the J is positive, it's an antiferromagnet. So that actually requires detailed calculation of the wave function overlap.
So we also have some questions about the second part of your talk. So
yeah.
One from Pavel. Is the susceptibility in monolayer chromium tribromide more singular than expected for 2D Ising magnet? If so, why?
Yeah, that's an interesting question. Indeed, so the 2D Ising magnet here, the exponent, actually this is for square lattice, is a 7/4, but I do not expect much change, compared to a honeycomb lattice, like in our case here. In this, so that's a 7/4 is 1.75, and here the measured exponent is 2.4. It seems to be quite substantially bigger compared to the 2D Ising case. And I think the simple reason is actually that the magnet here is actually not exactly the Ising model. Maybe actually in the literature, people believe it can be described by something called the XXZ model, so that you have an outer plane and a isotropy, but you can actually still rotate the spin into the plane by an not that big magnetic field into the system. So it's anisotropic. The exchange along the x direction or the in-plane direction is different compared to the spins aligned to the outer plane direction. So it's described by XXZ model. So you can think of it, the XXZ model is in between the Ising model and the Heisenberg model. A Heisenberg would be no anisotropy at all. And the critical exponent for 2D Heisenberg model, well, 2D Heisenberg model has no magnetic order, but the critical exponent for 2D Heisenberg model, if I remember correctly, it's about 3. And so this 2.4 is actually landing somewhere between the 2D Ising model and the 2D Heisenberg model. So we believe that's probably a signature of the fact that this material is not really described by an exact Ising system, but rather by a 2D XXZ model.
Oh. So thank you. And for the next question from Azo, have you tried to use heterodyne detection for your time domain terahertz setup? What are the benefits of homodyne detections?
Yeah, so the homodyne is we are mixing at the same frequency here. The heterodyne, then you actually have to modulate the light at different frequencies. And so we did not use any modulation in our measurement system, first of all, because we actually want to take the real-time videos of the magnetic fluctuations. So we did not actually introduce any modulation in the system. But I think heterodyne detection can also be done. We have to modulate at 2 different frequencies to carry that out. I'm not so sure whether there's any particular advantage of doing it in the heterodyne by going to 2 different frequency modulation. In this case, it certainly does not help us to see to take real-time images of the system, because these are fluctuating images. We cannot use a lock-in detection technique to detect it, so that I do not see a clear advantage of the heterodyne.
Okay, thank you. And also one question about the chromium tribromide. What's the resolution of the spin fluctuation map of the chromium tribromide?
Yeah, so it's basically given by the NA of the system. So in this setup here, the illumination NA, we are using a very small NA to keep the polarization being very good. But the collection NA, we are still using a full numerical aperture of the objective. And numerical aperture in our objective is about 0.6, so you can actually convert it into about 600 nanometer spatial resolution of the images. And the scale bar here, I forget the scale, I think it's about 5 micron, the scale bar here. Yeah, so typically we have about close to be, 600, half a micron to 1 micron spatial resolution in the system.
Okay, thank you. And I think due to the limit of time, we will take one last general questions. how to dope monolayer material.
Yeah, it's actually how to dope monolayer materials.
Yeah.
So it's actually trickier in this kind of system. Maybe a better example is actually shown here in the device structure. So typically you can just say, a monolayer semiconductor, you can just put an electrode that is touching the monolayer semiconductor, and you have a gate here. So it's a FET structure, a free effect transistor structure, that you apply a voltage into the back gates that you can actually introduce charge carriers into the system. But it is trickier in this type of system because the materials is extremely insulating at low temperature. So if you use the electrode that's just touching the material, there's almost no charge transport in the in-plane direction. That the charge just simply cannot transfer from one location to the other location because it's so insulating, the material with very low mobility. So what we actually have to do is to rely on interlayer charge transfer into the system. That's why we actually put the graphene totally covering the monolayer chromium bromide in this case. And to note that actually the chromium 3D bands has very large a density of states, so that you apply a gate here to introduce doping. It's actually introducing doping to both the graphene layer and also the chromium bromide layer. But you can work out the electrostatics, assuming that the density of states of the chromium 3D band is much larger compared to the graphene, then the majority of the doping will still go to the chromium bromide. And you can actually think of it is that I apply the gate between the two graphene, and the charge will transfer from the graphene to the chromium bromide and dope the system.
Okay, thank you. And sorry, we don't have enough time to answer all of the questions, and we encourage the attendees to email your questions to Professor Mak directly and to discuss for further discussion. And thank you, Mak, for your excellent talk. So we really appreciate it, and we will see you again tomorrow morning.
Okay, thank you.